effective dose equivalent. And what we do with this, it's kind of the same thing, and it's still the same units. We use REMS again. But basically it's the absorbed dose, or the RADs, and then multiplied by a quality factor, and then multiplied by a tissue factor. So in other words, there are some, we know that the different tissues in the body are more sensitive to radiation than others, but now we've quantified it, and so the effective dose equivalent takes that into consideration when we're talking about radiation exposure to a specific organ. Okay? So you'll see both of these being used. Okay? Over here I've given you a little, this is another calculation that you can use to show the effect of the radiation in calculating RDE. The last thing I wanted you to have down here is these other two terms called stochastic and non-stochastic. Sometimes they call this, this is a probability type of thing here, which means, you know, for example, your chance of dying from 1 rem of exposure is 1 in 10,000. Okay? But this is a statistical thing, which means not everybody who gets exposed to radiation is going to have that percentage of death.
Non-stochastic is guaranteed.
Yeah, non-stochastic, you know, if I give you 100 rads to your arm, you're going to get burns.
Got it.
Okay, everybody who gets 100 rads to their arms will get burns in the skin. So non-stochastic is what we call a threshold or deterministic effect. Okay? Stochastic is a statistical incidence. It's like with cigarette smoking. We know that if you smoke cigarettes, you have a higher probability of getting lung cancer, but not everybody who smokes cigarettes gets lung cancer. So that's what they mean by that. Not everyone who gets exposed to radiation gets cancer or develops DNA aberrations. So that's what we're looking at with that. Okay, so far so good? So if I give you a little quiz next week over radiation units, you'll get 100% on it?
Yeah, sure.
I think I gave you a sample quiz too to take a look at.
We're going to use the same sample quiz?
Huh? Oh, I might use the same one, but it's going to be, you're not going to think it's the same. Yeah, the other thing, I wanted to kind of hit a little bit of statistics before we move on here, because statistics are always fun, right? And because the rest of the California radioactive material license is going to be covering the quality control over all of the instruments that we're going to be discussing, but I need you to understand what it means by talking about a range or a statistical something or other. So do you guys have your statistics handout by any perchance?
Is it one of the ones you just sent?
What does it look like?
Okay, it looks like this one here. And then down at the bottom it has, yeah.
Is that from last quarter or this quarter?
Was it I said it last week, right?
Yeah.
It should be in the 352 stuff that I sent you. You don't have to panic yet because I'm not going to be giving you a test on it, but I want you to kind of get an idea of why statistics are important. In your math book, and again, you're going to love this, but in the math book from pages 51 to 79, we have all of these different things that we're going to be discussing. So you can be rest assured that you'll see questions from these chapters in upcoming tests. Okay? one of the things we've been talking about, the percent error. Okay, so when you guys put a source of radiation in for quality control, if it says on the vial it has 100 microcuries in it, this is what's stated on the vial. But it measures 89 microcuries. What's the percent error? Okay. Well, this is where you use that thing, because this formula, expected minus actual over expected times 100. Okay, so it's 11%. Now, what are we allowed here in California? 5%. Okay, NRC allows 10%. So are we in violation? Yes, technically we are. It's 11%. Okay? And some of the other things, now, why is Mr. Radke getting so excited about statistics?
Right, can you go back to the other page? I think you read everything down.
Oh, okay, which one here? This one?
Yeah, just real quick.
Okay.
Okay, thank you.
Now, when we're doing the calculate, this is on page 51 of the math book, so you might want to keep this one down. You notice it says percent error, percent difference, expected minus actual. And you notice that they have these two lines that represent absolute value. So that means it's whether it's negative or positive, it doesn't matter. You just treat it. So if I had 89 minus 100, okay, I still get 11%. Okay, so it doesn't matter. You know, you're allowed plus or minus readings on these things. So keep in mind that you know that's what we're looking at. So there's quite a few little problems in here for you to look at, and again, your board exams are not only going to ask you what the percent error is, but they're going to probably be asking whether or not the machine can be used. Okay, and that's what the key is here on this. So like I said, anything 10% or below, you're okay. But anything above 10%, you know, you're going to be in trouble. Okay?
So
But
it can't be used, so the machine has to be recalibrated or cannot be used at all?
it has to be repaired.
Oh.
Either repaired or replaced. If you can't fix it. Usually, you know, what you have to keep in mind is that we have that electrical source going to the gas, especially in your dose calibrator or in your survey meters. So sometimes the battery that's supplying that is going out. If you guys have a Cap and Tech dose calibrator, some of those have a voltage check that you have to use before you operate the equipment. It should read like 122 volts. So you do that first, then you do a background check, then you do your measurement of your constancy sources. You know, you do your, we typically use 137 cesium, 57 cobalt. Now remember, what do those two elements represent as far as quality control? They're supposed to be symbolic of other elements that we use routinely in nuclear medicine. Okay, which one represents technetium? The cesium or the 57 cobalt?
Cobalt 57.
Okay, the 57 cobalt, because it has 122 keV. Okay, so that means then what would the cesium represent?
No, molybdenum.
Okay, represents molybdenum. Okay, molybdenum has 740 to 780. What's the energy of 137 cesium? Actually, when it goes to 137 M variant. 662. Okay, so what we try to do is find radionuclides that have energy similar to what we use on a daily basis. Okay, in concentrations that we use. If you notice, your cobalt source is typically about 5 millicuries or more, or at least that's what it was when you first got it. You'll notice that the 137 cesium source is about 100 microcuries. Okay? Now, there is a third source that we use if you have iodine or if you routinely use iodine. Which one is that?
125.
What is it?
So 125 iodine?
No? Remember that? What's the energy of I-125? Yeah, it's about 35 and 27, isn't it? Okay, which is way far away from that.
159, it's 123.
Barium, 133.
Barium 133 is the one that we use. Okay, because it has an energy that's close to 365 or 364 keV. Okay, so you try to select radionuclides that are within the energy range of what you use. Okay, so this is one of the quality control tests that we use. But why do we need statistics for this?
It's random.
Very good. A long time ago, maybe last week, I talked about two types of error. The bad thing about error is that it's additive. So any mistake that you make is compounded by any other mistakes that may occur, either randomly or through what we call systemic error. So random and statistic. And where am I? And the other type of error that we have is systemic. Okay. The random error you have no control over. Okay. Random error is based on number of counts, for example. Let me give you an example. The way that we calculate random error is, let's say that you made two measurements, one was 100 counts and one was 10,000 counts. Okay, now you're probably thinking, well, there's no error in that, right? I made 100 counts per minute and blah, 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 blah. Okay, well, if we were to calculate the statistical error, basically it's the square root of the number divided by the number. Okay? So, if I had 100 counts, the statistical error by not collecting enough information is equal to 10% error. 10 over 100 is 10%, right?
Mm-hmm.
Okay, now the amount of error that I have with 10,000 counts, I have the square root of 10,000 is 100. 100 divided by 10,000 is 10. So 1% error, right? Okay, let's see how that would play out in a real life situation. Okay, let's say we have a patient that, now I'm going to